Hey guys, we are Group 1 and this is our bracket design project.
I'm Blake.
I'm Chad.
I'm Ben.
I'm Grayson. And we're Group 1.
These were the initial design specifications that we were given to base our bracket design project off of. As you'll see, we kind of deviated from these a little, but not much.
Here's our whiteboard. Shows the basic specifications of our piece we're working with. On the left is the punch forces and the thickness of it. In the top left drawing is the basic dimensions. The top right is the dimensions of the holes and elongated holes as well.
We began by using proportions of the given design to determine the sheet metal width and hole punch specifications, as can be seen in our more detailed design specifications of the sheet metal. First, we began the manufacturing process by using blanking to shear a near triangular workpiece with a relief notch as shown. We will then use the piercing process to remove the small circular holes near the bending line, as well as the elongated holes on the portion to be bent. Next, the oval shape along the hypotenuse and the circular hole near the center will be drawn to a fraction of the thickness. The larger hole in the center of the drawn circle will then be perforated, followed by a chamfer for widening. Last, we will use a press brake to bend the sides of the workpiece into place.
Next, as far as our parameters and features go, we did not alter the design of the original specification of the workpiece, but rather added more specific details to the hole and or punch placement using proportionalities in the provided bracket design. As far as our steel that we chose, we used AISI 1015 low carbon steel to manufacture our product due to its superior workability and machinability. Some considerations that we took into account while designing our steel was to have a clearance of 5 to 10%, and we're using 5% to reduce burr height, therefore reducing time of deburring and increasing the quality. The minimum hole diameter consideration, we had to consider that it needed to be greater than 20% of the thickness. The minimum wall thickness distance from hole to edge or hole to hole is greater than 2 times the stock thickness. Holes or slots must be 3 times the stock thickness plus the bend radius, and both bends will be at 45-degree angles to the rolling direction to minimize risk of fracture in both bends, meaning that we will roll at an angle across so as to not have one of our bends be perpendicular and one parallel, because parallel increases risk of fracture.
Here in the green portion is our calculations for the minimum radius, which is the radius at which fracture happens. We use this to make sure that our flange width was the correct amount.
For the annealing procedures with our particular metal, it normalizes from 1675 degrees to 1725 degrees Fahrenheit before air cooling. For full annealing at 1600 degrees to 1725 degrees Fahrenheit for furnace cooling. The process anneal after cold working at 1100 degrees to 1200 to 25 degrees Fahrenheit. It can harden, be carburized, not carburized, or it can be cased hardened.
Here are our calculations for our punch force regarding the perforations for our holes. Calculations, we used the punch force formula we found in the textbook. It's 0.7 times the thickness times the length times the ultimate tensile strength of our chosen steel.
As you can see, the larger the hole, the greater the punching force, which is why we decided to punch the smaller holes last, so as to not deform them in the punching of the larger holes. We're trying to minimize deformation of the holes being created. This concludes our presentation for our bracket design project. Please comment below, and thank you for your time.